Swayam Prabha. Digital India. Educated India.
In this lecture, I am going to discuss about planar kinetics of rigid bodies, and we are going to look at problems. I will show you through these problems some applications of these equations of translational and rotational dynamics. Just to recapitulate what we had discussed in the previous lecture, for a rigid body in a plane which is a prismatic body, and this plane x y I have shown in the figure contains the center of mass. The translational equation of motion, which is the extended Newton's second law, is given by this equation. The rate of change of linear momentum of the center of mass is equal to the net force acting on the body, and the linear momentum of the center of mass is defined like this: the total mass times velocity of the center of mass. And since this is the center of mass lies in the x y plane, its velocity is represented in this form. The equation of motion for the rotational dynamics, which is the angular momentum equation about g, is given by rate of change of the angular momentum about g is equal to the moment of all forces about g. And we have looked at the expression of the angular momentum about g. It is equal to the moment of inertia about g times omega. Under the simplifications that we have, the moment of inertia about g in this case of planar kinetics has become a scalar. Remember that we are considering prismatic bodies with omega perpendicular to the plane. If you write down the scalar equations, the component forms of the above vector equations, then you will have the three equations, three scalar equations, one in the x direction for the translation, another translation in the y direction, and the rotational dynamics equation, where alpha is the angular acceleration. Therefore, we can solve for three unknowns from these three equations. If you use a fixed point in the inertial space, then the equation, the translational equation, or the equation of translation of the center of mass, again given by the extended Newton's second law, and the rotational dynamics equation, that is the angular momentum equation, that is again in a very simple form: rate of change of angular momentum about O, the fixed point, is equal to the net moment of all forces on the acting on the body about O. And we define the angular momentum about O in the form that is written. We have discussed all these. If you again write the component form, we have two equations for translational dynamics in the plane and one equation for the rotational dynamics. Once again, remember that we are discussing prismatic bodies. There are of course little more generalization possible, but right now we are restricting ourselves to prismatic bodies. Only then we can express the rotational dynamics equation as a single scalar equation. For an arbitrary point P, the equation of motion, this is the most general situation we have. We have the linear momentum equation, the extended Newton's second law, and the angular momentum equation H p rel. Here H p rel in the case of planar kinetics reduces to I p times the omega vector, where I p is a scalar here, it is the moment of inertia of the body about p. Therefore, this is the equation. If the p point is a fixed point, it is a hinge, it is a fixed axis rotation, then the acceleration of point p goes to 0. Therefore, our equations simplify. We have these two equations, but only thing you have to remember that this force includes the reaction force at the hinge. Now, I will demonstrate application of these equations through some problems. This is the first problem taken from Merriam and Craig's book of dynamics. It says a passenger car of an overhead monorail system is driven by one of its two small wheels A or B. Determine which driving wheel will give greater acceleration without slip and compute the maximum acceleration if the effective coefficient of friction is limited to 0.25 between the rail and the wheels. Neglect the small mass of the wheels. This body, the passenger car, can be considered to be a prismatic body, and this is the first thing we must always check when before applying the planar kinetics, equations of planar kinetics. This is a box type of thing, and remember that these support points A and B and G, the center of mass of the body, that lies on a vertical plane, on a single vertical plane. First, we look at the coordinate system. We have the xy coordinate system and the free body diagram is shown here. First, I will start by considering that wheel B is powered. Therefore, in the free body diagram you can see that I have given a horizontal force F b at the hinge of wheel B, at the joint of wheel B, whereas wheel A is a passive roller, it only has the normal component. Now, equations of motion. We have, this is a rigid body, planar, prismatic. We have three scalar equations, two for the translational dynamics and one for the rotational dynamics. We will first start by writing the equations of translational dynamics. In the x direction, which is the horizontal direction, we have mass times acceleration of the car in the x direction is equals to net force in the x direction, which is only F b, the force at wheel B, because that is the only thing that is powered. In the y direction, since there is no acceleration, therefore, it gives only balance of forces. The rotational dynamics equation I am writing about point A. Why I am doing that? Because I have to find the basic problem here is to find out the condition on acceleration, so that there is no slip. Slip will occur only at wheel B, because that is the powered wheel. Now, if I have to check that slipping condition, I need the normal force at wheel B and the tangential force at wheel B. The tangential force, which is because of friction, that divided by the normal reaction should always be less than the coefficient of static friction. Therefore, I have to essentially calculate F b and N b, and all these calculations are geared for that. F b I can calculate from the first equation of translational dynamics, and if I write the rotational dynamics equation about point A, you will find that it will not have a contribution, moment contribution from F b, because the moment arm is 0, and then it will involve only N b, and I can solve the N b from here. Now, if I do that, rho A g, I have to find out this vector rho A g, which is this vector, this rho ag cross total mass times acceleration of point A. Now, acceleration of point A is same as acceleration of point G, is a non-rotating body. The body is non-rotating, there is no angular acceleration and no angular velocity as well. Therefore, rho ag cross mass times acceleration must be equal to net moment of all forces about A, weight contributes and the normal reaction at B contributes. And if you do this simplification, do the algebra, you can solve for NB directly from this equation. And from the first equation of translation dynamics, I have Fb. Therefore, I can take the ratio of mod of Fb by Nb, that should be less than the coefficient of static friction, and that gives me acceleration of the car when wheel B is powered to be less than 1.34 meters per second square for no slip. Now, let us switch to wheel A. Let us power wheel A and do the same calculation. If you the calculation, the translational dynamics will remain the same, only thing now the horizontal force because of the powering of wheel A, Fa, that comes in the translational dynamics, first translational dynamics in the x direction. Now, I write the rotational dynamics equation about point B, the center of wheel B, and if I again write down rho Bg, I express rho Bg in this coordinate system that I have taken. This happens to be rho Bg times mass of the whole car times acceleration of the point B, which is same as the acceleration of the car Ax. That must be equal to the net moment of all forces about point B. Now, Fa will not contribute, only Na will contribute, the normal reaction at A. Therefore, from this equation I can find out, I can solve for Na. From the first equation of translational dynamics, I have Fa, I have Na also. Therefore, I can take the ratio and I find that if wheel A is powered, the maximum acceleration is restricted to 1.13 meters per second square for no slip. Recall that if B is powered, then the acceleration was 1.34 meters per second square. Therefore, acceleration when B is powered is greater than when A is powered for no slip. This is for no slip. This is when the car has to travel towards the positive x direction. If it is to travel in the negative x direction, then the situation just reverses. So, that completes this problem. Let us move over to the second problem, again from the textbook of Merriam and Craig. It says the loaded trailer having a mass of 900 kilogram with G as the center of mass is attached at A, this point A which is shown in the figure, to a rear bumper hitch. If the car and trailer reach a velocity of 60 km per hour on a level road in a distance of 30 meters starting from rest with constant acceleration, compute the vertical component of the force supported by the hitch at A during this motion. Neglect any resistance at the relatively light wheels. We have this trailer, it is something like a box, again can be considered to be a prismatic body. The point G, the center of mass of the body, and this point A, they are located in the mid plane, vertical mid plane of the trailer. All dimensions are specified. Acceleration is specified in an indirect form. It is given that it reaches a velocity of 60 km per hour over a distance of 30 meter. First, we fix up our coordinate system and draw the free body diagram. Coordinate system is straightforward, x, y. Free body diagram I have shown here. There is normal reaction from the ground on the wheels, the weight, and at pin A we have in general two forces. I have resolved the net force in two directions, Ax and Ay. it starts from rest and reaches 60 km per hour over a distance of 30 meter. You can calculate the acceleration of the trailer. We have to calculate the vertical force A y. We will write the equation of motion as usual for a rigid body, the translational dynamics equations, which is the extended Newton's second law, is for the center of mass. Therefore, I need the acceleration of the center of mass, and it is in the I cap direction, A I cap, and I write down these two equations. The first is for the x axis direction, mass times acceleration is the force in the horizontal direction or x direction, which is A x, and the y direction equation is nothing but balance of forces, because there is no acceleration in the vertical direction. Then we come to the rotational dynamics equation. Now, here I have, for simplicity, for ease of calculation, I have chosen a point B. I have marked it here. Now, why have I chosen point B to write my rotational dynamics equation? First of all, this is the rotational dynamics equation about point B. I b is the moment of inertia about point B of the trailer, plus rho b g cross m a b, acceleration of B, that is equal to the net moment about B. Now, why did I choose B? Because the net moment about B will be contributed only by A y. A x will not contribute because the moment arm is 0, n and weight, everything, all these forces will not contribute because the moment arm, they pass through the point B. Therefore, the moment arm is 0. Therefore, through using just one equation I can solve the force in the vertical direction at the pin. Now, if I do that, rho b g, that is straightforward to find because all the dimensions are specified. It is this distance, it is 0.9 minus 0.5. So, it is 0.4 meter in the j cap direction, cross total mass of the trailer times acceleration of point B is same as acceleration of the trailer, the acceleration of point G, because there is no rotation, angular velocity, angular acceleration, or everything is 0, and that is equal to the net moment of all forces, only A y contributes. So, I have this, and finally, A y turns out to be minus 1388.9 Newton. In this calculation, actually I did not use these two equations, but I wrote them to show that we can solve other unknowns using these equations. As I mentioned, there are 3 scalar equations and we can solve for 3 unknowns. What are these unknowns? A x, n and A y. A y I have directly calculated from the angular momentum equation by choosing an appropriate point, the point B, and from the translational dynamics equations I can solve for A x and n. Let us move to problem 3. This shows a uniform slender bar of mass m and length L released from rest in the vertical position, and it pivots on its short flat end about the corner at O as shown. If the bar is observed to slip when theta equal to 30 degree, find the coefficient of static friction mu s between the bar and the corner. Part B says if the end of the bar is notched so that it cannot slip, find the angle theta at which contact between the bar and the corner ceases. The first part visualization is straightforward. Let me show you what is meant by a notched bar. Suppose this is that corner at O. A notched bar will look something like this. This is a notched bar. Here you have a sharp notch, and pivoting about this does not rely on friction. It is it is on the normal force which maintains the contact, and it will not slip because there is a notch and the corner sits on that notch, or the bar sits on the corner at the notch. Therefore, sliding is ruled out. The only way the bar can move out of this and lose this contact is that this bar moves out of this contact, which means the normal force disappears. We look at the coordinate system and the free body diagram. I take the plane polar coordinates E theta E r. You will notice that E theta is in the direction of increasing theta, as we had discussed in our discussions on kinematics. We have these forces, the weight of the bar and the reaction forces at the corner, in a force in the radial direction F r and force in the angular direction F theta. Now, equations of motion, the translational dynamics will be written for the center of mass as usual. Therefore, I need the acceleration of the center of mass, and writing the acceleration is straightforward. In this case, it is in the plane polar coordinates. Only thing, the radial coordinate is not changing. Therefore, I have this as the acceleration expression a g. I start writing the translational dynamics equation or the linear momentum equations, extended Newton's second law in this coordinate system. The first equation is for E r cap, mass times acceleration in E r cap is equals to the net force in E r cap direction. We have F r and a component of the weight expressed in this coordinate system. Everything has to be expressed in the coordinate system chosen. When you go to the E theta equation, the translational dynamics along E theta. So, this was E r cap, this is E theta cap. Mass times acceleration in E theta is equal to the net force in the E theta direction. We have F theta, it is in the negative E theta direction, as you can notice, and there is a component of the weight. Then the rotational dynamics equation, I have written it about that point O. Therefore, I need moment of inertia about O, it is 1/3 ml square times the angular acceleration is equal to the net moment about O. Who produces this moment? Only the weight. From the theta equation of the translational dynamics and the rotational dynamics equation, I can solve F theta. I just solve for theta double dot and substitute it here. Then I can find out F theta. This theta double dot equation here I have written also separately. So, theta double dot is a function of theta. Now, this can be easily integrated, because if I have to find out F r, I need theta dot square. For that, I need to integrate this equation. In order to integrate this equation, I write theta double dot as d theta dot dt, and that is equal to d theta dot d theta times d theta dt, and that means it becomes theta dot d theta dot d theta, and that can be written as d theta of 1/2 theta dot square. This expression I will replace in theta double dot, because now I have to integrate over theta on the right hand side. Let us see what happens when I do that. So, I have done this step and I solve for theta dot square, straightforward integration, and this theta dot square I replace in the first equation on the left hand side and solve for F r, the force in the radial direction. Now, I have f theta and f r in terms of theta. It is mentioned that this bar slips when theta is 30 degree. At the point of slipping, the tangential force at the contact divided by the normal force at the contact is equal to, so impending slippage is equal to the coefficient of static friction. If I substitute the expressions of f theta f r and use theta equal to 30 degree, I solve for mu s. Mu s is 0.188. The second part of the problem was, if the bar is notched, then when will it lose contact? As I have mentioned, it will lose contact when f r goes to 0. Let us see when f r goes to 0, then contact will cease. If f r goes to 0, I just put f r as 0 in this expression of f r that I have solved, and I find out theta, and that turns out to be 53.1 degree. Therefore, if it is a notched bar, it will not slip, but at 53.1 degree or 53 degree, let us say around 53 degree, it will lose contact. Let us move to the next problem. This is a very practical problem about door stops, where you should place door stops and why you should place them there. A door stop is placed at a suitable location to prevent the door from hitting the wall. Door stop is generally placed to prevent the door from hitting the wall, because the door might have handles here, and when it hits it damages the wall. Therefore, you have door stops. Okay, so it is to prevent the door from hitting the wall. Determine d, the distance is shown, this distance d, where the stop has to be put. Determine d so that when the door hits the stop at a certain angular velocity, the reaction at the hinge O is minimized. I have drawn the door at the instant it has just hit the door stop. Now, when it hits the door stop moving at a certain angular velocity, there will be an impulsive force at the door stop, because the door suddenly comes to a stop. There must be an impulsive force. You know that only an impulsive force can change linear or angular momentum suddenly. I have considered this plane polar coordinates, and the free body diagram is here. You have F s as the impulsive force at the door stop, O theta and O r are the reaction forces at the door hinge. We are considering only the forces in the E r E theta. There is of course the weight of the door, which is considered to be supported by the reaction along the hinge in the plane perpendicular to this figure. We are not looking at that those forces, right. We are not looking at weight or the hinge forces perpendicular to the plane of the screen. Let us write down the equations of motion of this door and see what kind of forces appear at O. Since it is a planar motion of a rigid body, prismatic rigid body, therefore, I have to first write the translational dynamics equation, which is the extended Newton's second law for the center of mass, and therefore, I need the acceleration of the center of mass, which is written here. I write down the E r component of the equation of motion. Mass times the acceleration in E r cap is equal to the net force in the E r cap direction, which is O r. Similarly, in the E theta cap direction, I have mass times acceleration in the E theta cap direction must be equal to the net force in the E theta cap direction. We have F s, which is impulsive, and O theta. Now, this angular momentum equation I have written in terms of the point S. The moment of inertia of the door about S times alpha, the angular acceleration, is plus this additional term rho s g, the vector from S to G cross mass of the door times acceleration of point S. And acceleration of point S now will have we have to find out because the door is rotating, and that is equal to the net moment about the point S. Who contributes moment about point S? Only O theta. OR has 0 moment arm. Therefore, this is minus d E r cap cross O theta E theta cap. If you look at the acceleration of point S, it can be written like this very easily. Straightforward kinematics. Substitute all those things in the rotational dynamics equation and simplify. This is what happens. I have written out this equation after simplification. So, I have some moment of inertia term into acceleration, angular acceleration is equal to minus d times the distance times O theta. Okay, this is our equation of motion. Now, there will be some force in OR direction, because this theta dot, as the door is moving, you will have some non-zero theta dot angular velocity. Therefore, I can do nothing about OR, but can I do something about O theta to minimize the reaction force? Well, this acceleration, angular acceleration, will not be 0, it is going and hitting, and there is a reversal of direction, there is an impulsive force, there will be acceleration, angular acceleration. How to minimize reaction force of the door at the hinge of the door? OR I cannot do anything, but O theta maybe I can do something. If I can make this term 0, if I can somehow make this term 0, then O theta will be 0. There will be no reaction, transverse reaction force at the hinge. Let us do that. So, for minimum hinge reaction, O theta is 0. I can find out IS, the moment of inertia about S, by writing by using the parallel axis theorem. This is about G plus m d square, m distance square. This is the distance of shift, is L by 2 minus that d minus L by 2, that is the shift. So, that square and minus this term is equal to 0. Solve for d, and it turns out to be a very simple expression in terms of the length of the door. It is 2/3 the length. This point D, this point S from that hinge is called the center of percussion, and this is very important in various other applications as well. For example, in a cricket bat, if a batsman can get the ball at the center of percussion of the bat, then the batsman will not feel any impulsive reaction of the ball, because when the ball hits the bat or the bat hits the ball, there will be an impulsive force. But if the ball is taken at the center of percussion of the bat, then there is no additional transverse force produced on the hand. Maybe though if you have played cricket and done batting, sometimes you feel a tremendous amount of impulsive force on the hand, but if you can get the ball at the center of percussion, it will be a smooth shot, you will not even feel it. You will have to only manage the weight of the bat and a little bit of force because of the rotation of the bat. The same thing is for the tennis rackets. If you do not want to have additional impulsive forces on your wrist, then you should try to get the ball on the center of percussion. This is also called the sweet spot for the bat or the tennis racket. So, this is the summary of what we have discussed. We looked at the application of the equations of translational rotational dynamics for plane kinetics of rigid bodies. So, with that I will close this lecture.